I'm here today to speak on the topic application of tropical geometry on subsemigroup of order preserving full transformation. So the first of us, we first look at the abstract. So when we talk about the subsemigroup, what we are trying to talk about on this research is to look at the application of tropical geometry to tie the tropical geometry and semigroup together. When we study this work, what we firstly did is to apply the tropical geometry on the subsemigroup of order preserving full transformation. And what we did is that by generating the elements of this classical algebra, that is the one from the subsemigroup of order preserving full, into the tropical algebra, and doing this, after doing this, the next thing we want to look at, study the multiplicity and see how do we find the multiplicity? The multiplicity was studied by first the tropical polynomial we got from the transformation semigroup. We have a GeoGebra app whereby we use, after applying the tropical geometry rules on them, then we use it to plot the graph. So plotting the graph, we are able to check the multiplicity, the roots from the graph, and from there we compare their heights. So that is what we try to do. So in the introduction. So in my introduction, the first thing is to first talk about the semigroup. As we have all have the knowledge of a group, that wherever I want to talk about the set, for a set to be a group, defined on a binary operation, there are three properties that must satisfy. That is, the associativity property must hold, there must be an identity, and there must be an inverse. Then in a semigroup aspect, we are only after one of the properties. That is, whenever you have a set that satisfies, defined on a binary operation in which the associativity is satisfied, there, we are talking about semigroup. Now, to talk about the transformation. Transformation is just a function, mapping of a function to itself. Whenever you are mapping a function to itself, you are already performing a transformation. So after talking about the semigroup, then we now want to talk about the transformation semigroup. This transformation semigroup, we have this transformation semigroup was introduced by Howe in 1995. And in studying this transformation semigroup, we have about three categories of transformations. We have full, we have partial, and we have partial one-to-one. Based on this research seminar, I only specify on the full transformation. So because with this, we have to define our transformation on a finite set. So that is what brought my definition of a finite set. Let S be the set of finite sets on the other standard way. Then we want to define our map the transformations. By doing that, we want to because whatever I want to compare, we are comparing the domain of alpha, which is a subset of SM mapping to image of alpha, must equally a subset of any set to be full if the im of alpha equal to S. This one is telling us to know how do we know the transformation that is full. Whenever the property, this point is satisfied, that is the im of alpha equal to Sn, then you are already talking about full transformation. And that is where that's the semigroup where we want to work on. And after knowing the full transformation, we move further by looking at this one of the subsemigroup. We have many subsemigroup of transformations. We have order preserving, we have order decreasing, we have order preserving and order decreasing, we have order reversing, we have orientation preserving. We have so many subsemigroup. But based on this research, we only want to work on order preserving transformation. So that is where I try to work on the order preserving transformation semigroup. So looking at the transformation semigroup, we look at the subsemigroup of other preserving in this food. Now, the next thing is to look at the one to move to the tropical geometry. The name tropical was colonized by the French mathematician, which is denoted by this symbol. We use this symbol to denote our tropical. So what we try to do here is to try to look at how we can apply the knowledge of tropical geometry into our existing transformation semigroup that we have been working on before. So in doing that, we need to firstly look at the classical algebra, that is what we call classical algebra, at our existing transformations. So what we do is to look at how we can degenerate our classical algebra into our tropical polynomial. And in doing that, we look at how we can apply the tropical geometry rules on this polynomial generated and see how we can use it to plot a tropical curve. After we generated this tropical polynomial, we use it to plot a tropical curve, and from there we are able to obtain, for us to be able to find all this multiplicity and height. So let me move on. So we define our tropical polynomial as this. Then the next thing is we have two ways of defining our tropical operation. When you want to talk about the tropical numbers, there are two operations. We define it on addition and at the same time on multiplication. If you look at my equation 2, whenever you have two functions, x plus y, that quotation is telling you that it is already in transformation, it's already in a tropical functions. So if you want to apply the tropical functions, say that wherever you have two functions, adding it together, the tropicals will say that the result will be mass of the x and y. That is, the maximum set between the x and y will be your addition of these two tropical polynomials. Well, if you define it on multiplication, that is my equation 3. That one is leading towards that when you want to multiply the two functions on a tropical rules, the multiplication of two functions x and y will give us x plus y. So that is the two operations we are using under the tropicals, the addition and the multiplication. And we define, when you want to define it on an infinite set, that is infinity, that is when you take an element, a single set in a tropical, and you are adding it together to an infinity number of negative signs, we are saying that the result will be mass of the what? Of x and y, which is already based on our rules of the operations. So that one is just telling us to the rules we are using to define our tropical operations. Like this, if you look at this, you can see that in the tropical operations, if you want to write the tropical of 2s, normally you say s plus s. But when you want to apply it on the tropical rule, it is not s plus s, but s plus 2. Because we are saying that when you are multiplying two functions together, it will be that function plus the second function. And at the same time, wherever you have 0s, it will not be 0, but s, because it is just two functions, s and 0. So that is just the rule we are using in our tropical. Moving further, then in looking at this tropical geometry, many researchers have worked on it. Like Bakare in 2012 studied the aspect of tropical geometry. Naimat in 2012 looking into the introduction to tropical algebraic geometry. So 2013 work on tropical intersection product in material farms. So Bakare and so many researchers has worked on this tropical geometry. So that is what we equally brought us to this work, because when we see that, we are equally look at how can we apply this our tropical geometry into our area of specialization, which is our transformation semigroup. In 2018, we studied the tropicalization of a potent element on this food transformation. That is, we apply our topical geometry rules on one of the subsemigroup of transformation, which is adrepotent. And we have the result. This paper has been published in one of the Nigeria journals. And for standard concept in the semigroup, we can contact the OWE, UMA, and as I was saying that what we try to look at in this research is to see how we can apply the tropical geometry on the semigroup. Now we have some definitions, that is some people that have worked sometimes that will make use of. Like the Brogali et al. In 2015, define a tropical numbers as a root of polynomial in one variable, which is defined in this set, and equally Brogali in 20 in et al. In 2015, equally define the multiplicity, how you can find our multiplicity between the two slopes, as m of I equal to the absolute of this, where our mi is representing the slope in each of the graph. So, and when you find the slope, we always look at the intersecting above the root. By the time I get to the example, you understand what I mean by the slope above the intersection. That is how the slope we are considering to find our multiplicity. Then you usually have the Brogali et al. That the results where these are part of the results he got, that is, you look at the finding degree, every polynomial of degree D has exactly D root when counted with multiplicity. That is one of the Brogali results in 2015. Now, UMA 210, what the UMA did is that he was one that firstly worked on the transformation, the order preserving food transformation. So we denote our order preserving food transformation as OTN. So then we equally define what is order preserving. When you consider a transformation in order preserving, the transformation is said to be order preserving when you look at the domain of the transformation as for all SY belong to the domain, such that S less than equal to Y imply S alpha less than equal to. What we are saying here that if the element in the domain less than equal to Y, they imply that the element in the image must equally less than equal to Y. So the SY is, S alpha is representing our images, while the ordinary S is representing our element in the domain. So looking for that, then when we study this, our first result we obtain is theorem 1. What we do is that after we consider the element of order preserving food transformation, the first thing we observe that we discover that every element in order preserving has the same multiplicity for each n. So how come all the elements in this particular subsemigroup have the same multiplicity? Then we justify our result by proving the theorem. So the theorem 1, here is the proof. We consider we are assuming that alpha is one of the transformation and beta is one of the transformation, shows that alpha A1, AN equal to SN, that is the elements in the domain are always the same under our transformation. But it's only the images that are different. So we look at that, then we prove our result of the theorem 1. Then we use, let me go straight to the example, because it's the example that we are used to validate our result, for you to understand what I'm trying to explain. So in proving, we discover that the multiplicity of that's why we are considering two different transformations, alpha of S and beta of L. We discover that their multiplicity are the same. Why? Let's go to the example. Look at the example 1. What do we do in example 1? We'll consider two elements of transformation, that is alpha and beta, taken from the order preserving transformation. Now, these are the elements we represented in terms of the charts. For this transformation, the alpha is S, 3 is implying that the 3 is fixed, 4 is fixed. So whenever you see elements that are not close, any mapping that 4 to 5, meaning that 5 is mapping to nothing. So this will represent our two transformation in terms of charts, that is in terms of this joint circle, by making use of the transposition and this joint circle in terms of transposition and semi-transposition. So after looking at that, now, after considering these two transformations, we take it to the polynomial. As I have said that our transformation is in terms of permutation. So the next thing is to convert our transformation to polynomial. So in converting our transformation, that is why we say we degenerated our classical algebra into classical polynomial. So by doing that, we have our alpha of S to be that, while beta of S to be this. So these are two transformations we are considering under full transformation. Now, by the virtue of the definition 2 and 3, where we are defining our tropical numbers under operation of addition and multiplication. So if you are applying that definition of virtue 2 and 3, we are able to take our polynomial into tropical roots. What we first say, by put this double colon is saying that it is already in a tropical. Now, considering this, since we are saying s raised to power 10, implying that if you want to take the polynomial, the tropical polynomial, it will be 10s, while 4s raised to power 9, it will be 9s plus 4. The next one will be 8s plus 6, 7s plus 7, 6s plus 6s plus 9, 5s plus, because we are applying those two definitions, addition and multiplication of tropical polynomial. And in doing that, we have it up to the last number. So then you did the same thing for the beta. By taking the tropical also, we have this. Now, after getting these polynomial functions, the next thing is to see how we can check their multiplicity. And we can only check this multiplicity by what? By plotting the tropical core. We have GeoGebra app that we use to plot this graph. And in plotting the graph, this is what we obtain. We're using our GeoGebra. We have our tropical curve of the alpha to be this. Now what we are representing, this dotted line in this graph 1 is representing our root. The root of each of the root of the slope. This one M1, we are using it to representing our slope. This is the slope 1. This is our M2 multiplicity 2. This is our M3. This is our M4. Now, while these dotted lines are representing our tropical roots, M1, R1, R2. So in this case, in this example, we have 3 tropical roots for this alpha of S, while we have our slope to be 1, 2, 3, 4. We have slope to be 4. And now, we use our slope to find our multiplicity of the roots. So from the graph 1 above I showed you, we are able to find our roots. The root of 1, we have it minus 10. If you look at the graph, if you trace our root of the graph, you see that our root, if you trace it down from the year, when we plot our graph to the GeoGebra, we discover that at this point, our R1 is intersect at the point of S is 10. At the point of S axis is minus 10. So we check for the root 2, we check for the root 3, and that is what gives us the result of R1, R2, and R3, as we see here. So from that graph, we obtain this at our roots. Now, after obtaining our root, the next thing is to look at the slope. How do we find our slope? We look at the slope by checking the line above the line above the intercept. The slope at that line will give us the slope for each of the roots. So when we check for the first one, we discover that our M1 at the slope at the line that we use to obtain the root 1 is 0, while our slope of M2 is 1, and our slope of M3 is 3, and our slope of M4 is 10. So after getting the root and the slope, the next is to obtain our multiplicity. And I've defined how we can obtain by what the Bogali defined that the multiplicity can only be obtained from taking the absolute multiplicity of R1 can be obtained by taking the absolutes of the slope of the 1 minus the slope of 2. So if you look at this one now, our slope 1 here we obtain is 0, while our slope 2 is 1. So it's 0 minus 1. I think we have taken the absolute. That is why we have 1 here. as our multiplicity of 1. And the same thing as our R2, we have that. Our multiplicity of that equally be what? So when that is slope of 1 minus 9, we have it to be 8. While the next one is multiplicity of R3, that would be slope of M3 minus M4, that is 9 minus 10, we have it to be 1. So in this, that we are able to find the multiplicity of this alpha of S to be what? 181. Which of the what? So which tell you that this one is of I2. So the same thing applicable to your second transformation we are considering, that which is beta of alpha. We plot its own graph also, and this is what we obtain. We obtain the root for its own, and we obtain the slope. Our M1, this one, M1, this is slope 1, slope 2, slope 3, slope 4. While our root is R1, R2, and R3. So that is how we obtain that. Then from this graph, we equally find the multiplicity for that beta of alpha as this. You can see that if you look at this element, these two transformations now, despite the fact you can see that the roots are not the same. We are studying this different multiplicity, different transformation, and we obtain this different roots and different slope. And in finding that, you can see that our multiplicity are the same. By the time we study, we obtain the same multiplicity for beta of alpha as what? 181. So it's telling us that when you consider any element in order preserving full transformation, we have the same multiplicity, irrespective of element, irrespective of the value of your root and the slope. That is the first of our results we obtain. Then we move further. That's our first theorem. Then we consider another example that by taking higher number of n, that is taking number of n to be 17 and considering taking their polynomial, taking their tropical, and plotting their graphs, we equally have the same result. This is the graph of the first polynomial routine, which is gamma, the graph of the second one, with different slope and the root. And look at our results. Look at the results of this one also. We have our slope to be, our multiplicity to 115.5. That is of the same multiplicity. The height of this multiplicity is equally the same. And considering this, look at the graph. That's why we are considering the different transformation and we obtain the different roots and slope. We are still able to have the same height of the multiplicity. That is our first finding we obtained from this research work. So we consider that and we have this. So you can see that we have different transformation, but we are able to have the same multiplicity. That's our first result. Now, we have our second result, which is preparation 2. The preparation 2 is telling us that what? Our result is saying that every transformation in order preserving full transformation from the value of any range from 1 to 3 are multiplicity of height 1. This one is telling you that when you consider all the elements of full transformation of height of n from 1 to 3, we have the same multiplicity of height 1. So we justify this our result also. This is the proof. After our proof, then we equally go by example to validate our results. Now, this is our third result, which is theorem 3. So what the result? We obtain this result said that for n greater than 4, that is when you are still considering the order preserving full transformation, the height of multiplicity in that have the same height of order 2. And if you look at the first two examples as you see, you can see that the height is of height 2. It can only have two heights. That is, the first one we have 181, the second one we have 115.1. So it's of height 2. So when we look at that one, we see that irrespective of any value of n, our multiplicity will always be height 2. So we prove that one, which is our theorem 1, and this example 1 has already justified that. So we move further by looking at the examples. We consider the elements of order 4, order preserving, taking their tropical, after taking their tropical polynomial, taking into the tropical classical polynomial and plotting their graphs. So this, look at the graph of this delta, and we find their multiplicity. Look at their multiplicity. So the multiplicity is of height 1. So we find their multiplicity of 1 to 1 for the theorem 3. So because we have said it's of height 2. So you can see that this one is of height 2, that is 1, 2, 1. We can only have the height 2. We are talking about the number of elements we can only consider here 1 and 2. That is why we call it is of height 2. So moving further, looking at the next example of example 2b, by taking higher number of n and look at taking their polynomial, taking their tropical polynomial, and see whether we have the same I2 for that transformation also. This is our tropical curve plotting gotten from the GeoGebra app we used to plot. Then in doing that, we can see that we have the multiplicity of height we have here is 191, which is equally of height 2. The first one is 121, but it's equally of height 2 because we can only have 1 and 9. We can only have 1 and 2. So they are just 2 elements. That's why we call it I2, which validates our theorem 4. Then looking at further, look at the example 2c. So example 2c is by taking higher number also. In this case, you can see that we take as number of n to be 24. Look at the transformation element we consider. We take our polynomial, we convert it to polynomial, classical polynomial. We obtain this. Then by taking by virtue of definition 2 and 3, we are able to take their polynomials, the tropical polynomial, and we have this as our tropical polynomial, and we use that our tropical polynomial to get this graph. So look at this graph. Looking at this graph now, we can see that all these dotted lines are the roots we obtain. So we have 3 roots in this graph, and we have our slope M1, M2, M3, and M4. So all these are the one that's represented. And we only check the slope of one that's above the root. So you can see that we did not check the below. We only check the slope that's above the root of our graph. So looking at that, we consider another graphs, another transformation, and see whether that one we call it Gifford. Look at this one also. In taking the multiplicity, finding the multiplicity, we are able to obtain the multiplicity of I2 for this, which is telling us that irrespective of number of n, we are considering your other preserving transformation, we always have the multiplicity of I2. So that is our result. Then we have another result, which is what? Theorem 4. What this result is telling us that we want to consider the order of this multiplicity altogether. The order of multiplicity of other preserving transformations. So, and the result is telling us that the order of multiplicity is of 1, n minus 2, and n. That is for all n greater than 3. When you want to find the order of multiplicity of any element in other preserving food transformation, is always of this form. And here is the proof. We have the proof to validate our result also. So in proving that, because of those examples we have done so far, your theorem 1 and prepositional, you can see that this our result is actually true. Because we consider in theorem 1, we consider the elements whereby we consider the height of n equal to between 1 to 3. We have that we are able to have the multiplicity of height 1 for that. That is so that wherever your n is ranged from 1, you only have your multiplicity to be the order of the multiplicity will always be 1. But whenever your I range from 2 to 3, the order of your multiplicity will always be equal to n minus 2. And if you look at the example we did above, even where we consider our n to be 24. If you look at that, we obtain our multiplicity to be 122, 1, which is of height 2. By the time we put it here, it's telling us that whenever your n is 24, that will be 24 minus 2. Then we have said that it's of height 1, we always be 1. So then to obtain your 22, meaning that wherever n is 24, that 24 minus 2 we give us 22. So which will give us the result of one of the example we did above, we have done above. So it's telling you that irrespective of the value of n, you can obtain your order of the multiplicity by using this, our results. So this one is telling you that the multiplicity of any element of the order preserving transformation can be obtained by using their general formula. So we use example to validate our result by taking a small number of n, taking the lower number of n of 3, taking their polynomials, taking their topical, plotting their graph, see their multiplicity. We obtain the roots. Our root is 3, which are the dotted line represented our root, while these are the slope of the graphs. So now looking at this, find the multiplicity and see what we obtain. So that's why we have different roots. In this one, we have R1 to the minus 2, R21, R3, and we have different slope for each of the roots. But finding the multiplicity, you can see that we are able to have the multiplicity of height1. Look at it. So we can see that we look at it. We are able to see that our multiplicity of this particular transformation is what? Is 1. It's of height1 because we have 1, 1. So it's of height, meaning that wherever your value of n range from 1 to 3, your multiplicity will always be of height1. That is, we only have height, the order of multiplicity will always be 1. That is what this one is trying to tell us. Now, if you take your value of n to more than 3, that is, we consider n to be 8 here. This is our transformation. Taking the polynomial, we have this. Applying the tropicals, algebra rules, we have this. Using this tropical to plot our graphs. This is the graph. And in the graph, we have 3 roots. We have 4 slopes. And the slope are different. We can never have the same root. Look at this one. In the previous one, we have our R1 to the minus 2. In this case, we have our R1 to the minus 6.3. Our R2 to the 1.6. Our R2, you can see that they are different roots, different from the previous one we did. And we have the slope as equally different. And when you look at the multiplicity, we find the multiplicity 169, 161. So it's telling us that wherever your value of n greater than n, your order of multiplicity will always be n minus 2. That is what that is telling, because as our n is 6, this one is telling you that 1, which is standard, for this one is n minus 2, that our n is 8, so n minus 2 will be 6. That's why we are able to have 1 to 6 here as our multiplicity. So we look at the third example, considering the highest number of n, which is n to the 30, and see what will happen to the, is it going to be work for irrespective of value of n? That is what we are trying to check. That is why we are taking highest, lower number of n, middle number, and we are equally taking highest number of n. And taking highest number of n, look at their polynomial, and look at their tropical, and see our graph. Look at the numbers of lines we are able to obtain. And despite the number of lines we obtain, we still able to have the root to be 3. We can see that we still have 3 as our root. Root 1, root 2, root 3. And our slope is always equal to 4. And let's look at the multiplicity. Is the height of multiplicity the same? So look at it. The height of multiplicity is still 2. So since then, this work is telling you that irrespective of any value of n, your height of multiplicity will always be what? Will always be of I2. So these are all what we obtain in this our work. Now, our remark. Our remark is not telling you that the sum of multiplicity on every transformation of order preserving full transformation is equal to the degree of its transformation. Let's confirm this remark by looking at our previous example. Let me take look at this example. What we are saying here that the sum, when you sum all the elements you obtain, look at this n. When you are consider our n here, we consider our n to be n equal to 30. Now, which is n. Now, by the time when you now sum all these multiplicity roots, all the height of multiplicity we obtain, when you sum it together, you can see that your result will equally be, look at it, 1 plus 28 plus 1, which is equal to 30, which is the same thing as the number of n. So that is what the remark is telling you, that the sum of the multiplicity will equally equal to the degree of the transformations. So this is what this is our sum of the results we obtain. So in conclusion, in this our paper, we have shown that for each n, the multiplicity of elements in subsemigroup of order preserving, that is OTN, are the same. Because we are able to consider for n equal to 1, for the lower number of n equal to 1 to 3, n equal to 3, between 3 to highest number, we have seen that their multiplicity are always the same. So for each value of n, they always have the same multiplicity. And we equally look at that the order of their multiplicity are equally 2. The order of the multiplicity for the value of n from 1 to 3 is always 1. Our example has equally validated that. And for n greater than 4, we always add the order of multiplicity, irrespective of any value of n, to be of height of what? To be of order 2. That is, the height of multiplicity is of order 2. So this is where our result is. So here are the references that you can check for the further of the work. Thanks for listening.